Yeah, comes on everyone. Start off. Let's start off with a question. We have a planet here, mass m, radius r. In case 1, a particle of mass m is projected with speed vu is equal to root over gm by 2r. So this is projected radially. In the second case, you projected the same particle with a speed of root over gm by 2r, but this time the angle is 60 degree. Find the maximum height from the surface of the planet. Be careful, you can't use u square by 2g. Gravity is not constant. Let's get this. It's a good one. The first one is a proper main level question. R by 3. First part is easy. So this thing reaches somewhere here and finally it stops. Let this be height h. This is your state 1. This is your state 2. Energy conservation. Energy in state 1 is equal to energy in state 2. Initial energy, potential minus gmm by r. Potential into mass is potential energy. Kinetic energy of mu square, u is gm by 2r. At the highest point, the potential energy is minus gmm by r plus h, and kinetic energy is 0. Gmm goes off, and you end up with 1 by r plus 1 by 4r. This 1 by r plus h, and this is minus 3 by 4r. H is equal to r by 3. Easy. Straightforward substitution. That's why it's a proper Menzel equation. The h is the height from the surface. What will you integrate exactly? You can integrate. Same aayega. You must have goofed up. You took force. Jm by r square is equal to ma. A you wrote as v dv by dr. And when you integrate this, what you found is literally change in energy only.
mg नहीं consider करना.
अरे God. mg आया कहाँ से?
So बीच में I wrote mg plus gmm by r
नहीं नहीं वही बोल रहा हूँ. अच्छा, mg is giving by whom?
Yeah.
Let me ask, if you're standing on Earth, who is giving that mg? The Earth, if you're confused, right? And who is giving the gmm by r square? The Earth. So what is Earth doing 2 times?
अरे.
Understood?
I'm so dumb now.
होता है. That is what science people do. We do everything, and then so when we forget to plug the power, put on the power supply. One of my friend was there. वो तो all India top 100 ranker था. He brought a new computer system, assembled everything. It was not working. And he said like, यार नया system रे, I spent 40,000, काम नहीं कर रहे. He was so worried. We also went. I also checked everything. I said, yaar, haan re, everything is fine, nothing working. I called my friend. He also checked everything working. Then one senior came and said, idiots. I said, okay, why is he calling idiots? What we did, वो UPS power supply होता है ना, we took this power supply and connected it to the same thing. So we are creating a self-sustaining system where energy does not come from outside. So the senior got it out. अरे power supply आ कहाँ आ रहा है? So everything is fine. So we connected the same thing. Next thing. Then what about the V part? नहीं है आर्यन, इतना अच्छा आंसर नहीं आएगा. गॉड, सेकंड वन. You won't get a good answer. I think you should write the equation and leave it. Quadratic आएगा. Now, one of the common repeated broken tape recorder dialogue. Remember? What is that? Anyone remembers?
You should know when you make a blunder.
नहीं, वो नहीं है. Regarding the question, academic one. वो तो है. That is a different one. If something is not going in a straight line or a circle, what to do? This is going to go differently in some weird path. Conservation of angular momentum and energy. Keep that in mind. If you're not going in a line, you're not going in a circle, there is no other way we can do other than conservation of angular momentum and energy conservation. These kind of things, when you keep on practicing, right, you will learn certain words and certain terms. When you see the question, you get a feel, "Arey, isme aisa karna hai." These are important. If you don't have those kind of things, you won't get speed in the exam. So this will go in some path. Actually, it is an ellipse. We will see later on, but it is okay. So finally, at this point, this is your farthest point. Velocity is not zero. It will be perpendicular. That much I know. This guy would be r plus h. H is the height from the center. This is 60 degrees. State 1, state 2. Torque about the center of the planet is 0. So you can conserve angular momentum about the center. So mu cos 60 into r, mu perpendicular r, is equal to mv r plus h. Or you could have taken small r directly, and then later on you can substitute if you want. The mvr. So that is one equation. UR by 2 is equal to VR. Then energy conservation. Energy in state 1 is equal to energy in state 2. Initial energy of mu square, that would be gm by 2r. Potential energy minus gmm by r. Here this potential energy minus gmm by small r plus half mv square. So take this v from here and substitute, you get a quadratic. You solve this, you'll get r from here. Clear? You will get 1r positive and 1r negative also. So that is because the max doesn't know that there is a chance this will come and collide like this. That would have been a complete path like that. So the max is trying to find the other smallest distance. Because the equation is saying, find me the velocity or find the distance when the velocity is perpendicular, isn't it? That is what we are trying to find. Max doesn't know you're talking about a satellite, you're talking about something. What you asked Max is, give me a point, state 2, where velocity is perpendicular to r. There is 2 points which will happen like this. One here and one here. But we know this is going to collide here, so we don't take the negative root. Clear with this thing? 2 equations, 2 unknowns you can solve. You'll get the answer from there. Maybe I think you will get a good answer here, I guess, because u ka value is given. Maybe. Clear? But still you get a quadratic. Next one. Okay, someone did get r is r4 plus root 13 by 3, it seems. You guys can verify. Clear? Next one. We have a planet of mass m and radius r. Very far there is a comet which is going with speed u. So from the center, this distance is a. So the question is, as you're getting closer and closer to the planet, it will get attracted by the planet. So find the minimum speed so that it does not collide with the planet. Think of like this. If you have zero velocity, what will happen? You'll go and straight hit the center of the planet, isn't it? If you have little velocity, you'll hit here. If you have very high velocity, you'll go off like this. So that means there is a minimum velocity where you will just miss the planet. So there is a minimum velocity where you will just graze the planet and go off. Find your minimum. Hmm. Yep, something like that. Pretty clear again. It's not going in a line, it is not going in a circle. Conservation of angular momentum, conservation of energy. नहीं रहा Aryan, you got something weird. This is your state 1. This is your state 2. Velocity is v. Conservation of angular momentum. Remember, angular momentum is mv, r perpendicular. So perpendicular distance is a. Mu a is equal to mv r. R is the perpendicular distance here. You don't care about the actual distance. What you care is only about the perpendicular distance. So this is conservation of angular momentum. Energy conservation. Initially, you're very far, so potential energy is 0. Kinetic energy is half mu square minus gmm by r plus half mv square. This is energy conservation. Take v from here, which is ua by r, and substitute here. This would be u square by 2 minus gm by r plus u square a square by 2 r square. So you end up with u is equal to gm by r 2 by root over 1 a square by r square minus 1 ka root, something like this. You can simplify it further. That's the thing. And technically, you can see here if a is equal to r, means you need infinite velocity. Means definitely you should be away the. So the question would be like this: find the area in which the comet should not enter, getting it so that it does not collide with the planet. Basically, this is a danger zone. If any comet is within this area, pi a square, it is definitely going to hit the planet. So the other way around. So they can frame questions like that. If a comet with speed you enters this circle region, you're gone, meaning it's definitely going to hit the planet. You state took a distance is capital R, na? Why you need to do that? You said you're just missing the planet, isn't it? So you're grazing. All clear with this? Any doubts on this? Udayan, Swastika, clear with this? Maulika, Saina, clear with this? Maulika, clear? Vartika, Ali, Anika? Great. Next one. Variation of gravity. Acceleration due to gravity, small g. So when we kept on saying in an element all mg, what is exactly this m into g? So when you take any object on a planet, the planet attracts with a force of g mm by r square. This is what we have been calling so far as mg. Since we are mostly on the surface of the planet, the gravity doesn't change. So that small mg, which is written as g capital M by r square. So we get g is equal to gm by r square. This is their acceleration due to gravity. So this depends on planet to planet. This can be also written as g density 4 by 3 pi r cubed by r square 4 pi rho g r by 3. So if you're talking in terms of density, you are going to use this one proportional to r. If it is mass is constant, then 1 by r square. Now for different planets, this is different. For G Earth, if you substitute the value of the mass of the Earth and radius of the Earth, we end up with 9.8 meters per second. If you go for Jupiter, if you substitute the mass of the Jupiter and radius of the Jupiter, this thing turns out to be around 62.1 meters per second square. No need to remember, I'm just saying. Same thing if you talk about Moon, it is almost 1/6. So this g which we talk about is different for different planets. So basically what we're talking is acceleration only on the surface level. This is the acceleration due to gravity on the surface. If you go up and down, this value won't be constant. Clear? Now, how does this gravity vary? So there are three ways it can vary. One, when you go with height. So if you take height h above the surface, the gravitational force becomes gmm by r plus h whole square. So we're going to call this m g apparent is gmm by r plus h whole square. Will cancel. So g apparent is gm by take out r square common. You end up with 1 plus h by r whole square. So basically this is the gravity on the surface by 1 plus h by r whole square. This is the actual formula with height. In this, there is an approximation. If h is much, much less than r, let's say radius of the earth is 6,400 and we are talking about 10, 50 kilometers, 100 kilometers, then we can use a binomial approximation. G apparent will be approximately, this will be G surface into 1 minus 2h by r. Now be careful, don't use this anywhere because people actually mess it up. So use this only for very small heights. So this thing works everywhere. Second thing with depth. Now again, same thing. If you go into the earth, even then the gravity varies. So if you have gone to depth d inside, that means from the center, this distance is r minus d, which is your small r. Then we know m into g apparent is nothing but field, which is g m small r by r cube. That's a field inside a solid sphere into mass m. And if you substitute here, you end up with g apparent is g into small r is r minus d, 1 minus d by r. There is no approximation here. It's a straightforward formula. It is a linear function. So the gravity actually drops linearly. This is with the depth. This is with the height. You should definitely mark up the formulas. Okay. Next thing, variation because of Earth's rotation. We have done this in circular motion. So if you take a person somewhere here, This is theta. So theta is called colatitude angle. So if theta is 0, it is equator, theta 90 is pole. So if you look at the forces, the gravitational force will be toward the center of the Earth, which is G, which is mg. The centrifugal force will be away from the center of the circle, which is m omega small r, where small r is this. So small r will be equal to r cos theta. This angle is also theta. So this person will feel the gravity is down, which is the center of the Earth, and this component would be m omega square r cos theta. So mg apparent would be mg minus m omega square small r is again r cos theta into cos theta. You get a cos square theta. Let's have a look at this. So these are the three cases the gravity varies. Clear? Let's say a question. A barometer shows 75 centimeters for pressure P naught on Earth's surface. At a height h above the Earth, it shows 90 centimeters for 2 P naught by 3 pressure. So as you went high, the pressure also dropped. The gravity also changed. To find height. A pendulum has time period T on surface. At what depth from the surface time period becomes T. A capillary has height h. On Earth's surface. So basically, wherever you can think that G came, you can literally bring every equation. Find the capillary rise. At a height of 3r from the surface. Assuming all other conditions remain same. If the G apparent on surface of equator is equal to G apparent at a height h above the North Pole. Assume h is much less than r. Find omega of the Earth. There, let's get them all. So there you can bring barometers, pendulums, capillary surface tension, whatnot, everything. It's all just based on what we did. Get them all. Give them a try. You got 2 minutes. I'll be just back in a minute. Something is burning in the house. I'll be back in a minute. I found the reason. My wife is doing something weird in the kitchen. She's burning some pot. She's making some tandoori chai, it seems. I don't know what the hell that means. Okay, let's see the first one. Barometer. Hope you remember the formula. H is equal to pressure P naught by rho G. This was the formula. So here density is constant, so H is proportional to P by G. I'll just call it P. So we have height here H1 by H2 is P1 by P2, G2 by G1. So initial height is 75 centimeters, final height is 90. Initially pressure is P naught, final pressure is 2 P naught by 3. This guy is G apparent and this guy is G. P naught will cancel. That would be 5 by 6, 3 by 2, G apparent by G. So G apparent would be 2, 3, so 5 by 9G. Now, how do you know whether you have to use the approximate formula or the normal one? Just look at that thing. Normally, the value used to be G. It became now 5G by 9. You changed it by 4G by 9. That's a huge change. There's not a small error. So you can't use approximate formula. You have to use G1 plus H by R whole square. So GG will cancel on both the sides. You end up with 1 plus H by R whole square is equal to 9 by 5. So H is equal to root over 9 by 5 minus 1 into R. Check. Yep. You can't use the approximate formula because the change is not small. When we say change, we are talking about 1 or 2%. That is a Bernoulli approximation. That's how we do that. Second question, time period pendulum became 3t. Try, I'll give you a minute. Keep going. I think now you got the hang of what to do. You just have to find that G somehow and then you're done. Put it in the respective formula. Next one, B1, the time period of a pendulum is 2 pi root over L by G. So this is proportional to 1 by root G. So if T became 3 times, that means G must have become 1 by 9. You're going into the earth, so the formula is 1 minus D by R. So depth is 8 R by 9. Third one, capillary height H, 3R height pe. What is the height of the capillary? Keep going. These are like standard bits level, mains level questions. These are. Everyone should try. Give it a try. Next page here. The next one. So G apparent is G by 1 plus H is 3R by R whole square. That is 1 plus 3 4 square, so G by 16. And we know the height of the capillary is what? 2S cos theta by rho GR. So proportional to 1 by G. Therefore, the height becomes 16 times. Assuming you have enough length of the pipe. If you don't have enough length, you know what will happen? Tube of insufficient length. The next one. Now, the person on the equator, he will experience what acceleration? G apparent is G minus omega square R. If you go height H, so we are combining two of them. What is the G apparent here? Since you said height is very small, I can use binomial approximation, 1 minus 2H by R. And now you're telling me these two are equal. So G minus 1 minus 2H by R is G minus omega square R. GG will cancel. We get 2GH by R is equal to omega square R. From there we get omega is root over 2GH by R square. Easy? There, literally we used all the formulas. The approximate one, the normal one, the depth one, the rotation one. So on the equator, the gravity variation is due to rotation. On the pole, there is no rotation because R is 0. But due to height, there is a variation. And you're saying these two are equal. All clear? Next one. Any doubts, please ask me. Udyan, Vidyut, clear with this? Udyan, clear? Palaksh, Rehan? Next one, let's see. We have a planet here. Mass M, radius R, rotating with omega, which is root over G by 4R. A is a point on the surface on equator. Then, due to internal forces, this thing got compressed to half the radius. Mass is same. Due to internal forces, it compresses to R by 2. The mass is same, and this became R by 2. Again, if you take the same point here, A is still on the surface. Find the G apparent before and after. Find the ratio of G apparent before and after. I hope you realized what I did. I brought rotational mechanics into it. Let's see. This is a good one. You just have to be careful with the calculations. There are just too many variables. Try. Sana, give it a try. Solving. Why are you chilling out as if you're in a park? Chalo, try. 3/8, 3/2. Lakshika, check your answer. Let's say you're right. Others, give it a try. Got a minute. Something also changed there. You didn't realize. Yeah, 3/8 is the answer. So first thing, this will be omega dash conservation of angular momentum. I1 omega 1 is equal to I2 omega 2. 2/5 mr square omega is 2/5 mr by 2 whole square omega dash. So we get omega is 4 omega. So this guy would be 4 times root over g by 4r. Or you can simply write as 2 times root over g by r. Now, at this point here, what is g apparent? So initially, g initial is g ka value minus omega square r. So this would be g minus omega square is g by 4. This is 3g by 4. Fair enough. But you're forgetting something here. What is g exactly? G is gm by r square. Now the radius of this planet has become r by 2. That means on the surface, the g itself has changed. Now g on the surface is gm by r by 2 whole square. So this is actually 4g. Are you getting it? Because the planet shrunk, the point A has come closer. So g on the surface is not g anymore. G on the surface is 4g. I hope you're getting the catch. That was the difference. Initially, A used to be here. Now A is not there. A is much closer. So gravity is increased. The radius has become half. The g on the surface is 4g. Now g final apparent would be g on the surface minus omega square r by 2. Everything changed. So g on the surface is 4g. G omega square is 4g by r into r by 2. That would give you 2g. There. So g initial by g final 3g by 4 and 2g. 3 by 8. Hope you're getting the catch. So three things happened actually. One, omega changed. Second, the radius changed. Third, the g surface changed. So all these three terms are different. Clear? Arjun, Aryan, clear with this?
Yes.
Adrit, Aditya, Ali, Saina, clear? Yasha, got this? Great. Turn in the page. Satellites. So what's a satellite? Any object that revolves around a planet in a stable orbit. Now, when you say stable orbit, we call them bounded orbits. So basically, bounded orbits are these are closed orbits like circle, ellipse. You have unbounded orbits like we hyperbolas and parabolas. These things don't come back; they'll go off. And the second thing, their total energy is negative. Means if you want to separate them, you need to provide energy to separate them. So keep that in mind. So whenever say someone's satellite is going, you can be sure the system is bounded. That means the total energy of the system should be negative. Now, if you take a planet here, and let's say this is going now in our portion, technically we have only circular orbits, but then again, advancement they can ask you elliptical orbit also. We will see few of them also. So the forces would be gmm by r square. The centrifugal force would be mv square by r. So gmm by r square is mv square by r. So do remember the process how we derive, because later on we'll see some questions, where they will say the gravity is 1 by r. So v is equal to root over gm by r. And what's the time period? Time period is 2 pi r by velocity, which turns out to be 2 pi root gm r power 3 by 2. This is the time period of the orbit. And remember, this m here is the mass of the planet, not mass of the satellite. That means if you can find the distance of the satellite from the planet, and if you can find the time period, you can find the mass of the planet. That is how we know what is the mass of the Earth. No one actually takes the Earth and puts it in a weighing scale. Note on those formulas, we are going to need them. R is the distance of the satellite from the center of the planet. Clear? Turn in the page. If
Just 2 minutes.
satellite is very close to the planet, the velocity becomes root over gm by r. You can multiply and divide by r. This becomes root gr. This is called orbital velocity. So basically, the velocity when you're pretty close to the planet is called orbital velocity. For Earth, this thing comes to around 8 kilometers per second, 7.8 something. Now, in the satellites, right, there are some special satellites called geostationary. Geostationary orbits. So basically, the time period of the satellite is equal to the time period of the planet. So on the planet, it feels as if it's fixed in the sky. That's why we call it geostationary. It feels it is stationary from the planet perspective. Now, if you take for Earth, the time period is 2 pi root gm r power 3 by 2. And if you substitute here, this is 24 hours. This Arca value comes to approximately 42,000 kilometers. So if you can launch satellites and put at this height will be 36,000 kilometers roughly. Then you will think it is stationary. It's very expensive. To send a rocket to that high, you need a lot of fuel. If you see, right, the International Space Station, which we have, is at a height of 600 kilometers roughly. So all the satellites that we launch are only at a height of 400, 300 kilometers. Within 200, 300 kilometers, the space is almost gone. It's almost near vacuum. So it is actually, and now because of this, what happens, even though it looks near vacuum, there is still some air resistance. So the satellites are always, being decelerated and they're trying to come towards the Earth. So you have some rocket thrusters inside, which will keep on adjusting the path to maintain them. So the reason why satellites get destroyed, is like because the fuel gets over. So this is what happens. The satellite is going. Because of the air resistance, it will go out of the path. So this was the path it should go technically. So every time it tries deviates the path, they use thrusters and get it back on the track. Again, it will deviate after a few months or something. Again, they'll put it on the track. Because you're launching them at a height of 300 and 400 kilometers. So a satellite lifespan is around 2 years. So after every 2 years, when the fuel is about to get over, they take the thrusters, put them towards the pointing towards away from the Earth when you're trying to launch them towards the Earth, and they crash the satellite into the Pacific Ocean. Meaning, if the fuel gets over, right, and if you leave it like that, it will come and fall on a city. Just imagine. Today, a satellite landed on Mumbai ka highway and cars got damaged. Doesn't look great. So, in order not to get all those things, they just crash it into the Pacific Ocean. If you go and search now, you will find this thing. It's called a graveyard of satellites. That point on the Pacific Ocean is the farthest point from any nearby land. So they specifically go and crash the satellites there with the last amount of fuel. So just imagine it is cheaper to launch a satellite for every 2 years than actually putting a satellite in 42,000 kilometers orbit. The fuel becomes so expensive. And on top of it, every 2 years, if you can change it, matlab, you can introduce new technologies that way. So normally we launch them at a height of 300, 200 kilometers. And that's the problem also. Another issue with that is if you're launching them only till here, this satellite has only this much range, isn't it? Tangentially. It can cover only this much area. So when the satellite goes away this way, you don't have access to the satellite. So we have a GPS system. GPS is not the thing which you actually use in your phone. That actually uses a cell tower. This GPS thing, right? Military GPS actually. They have 24 satellites. So when this goes out of the link, another satellite, two satellites are always, on top of the region you want. Did you guys see the movie Parmanu?
Yes, sir. उसमें घूमता रहता है.
In the movie full, if you seen it, that was the whole story. The US people, right? They're tracking of that area with their satellites called Lazarus satellites, and in that he says that only these satellites go out of this region, and when the second satellite enters, there's a gap of 1 hour. 1 hour in the morning and 1 hour in the evening. We need to do the work and get it done by then. That was the whole premises of the movie. That the satellites, right? They give you 2 hour ka window every day. This is what happens. So the only countries to have is one is US, one is Russia, third is the European Union. European Union use it for non-military purposes. It's very expensive to build and maintain it. India does have, we have few military satellites. Things go on like that. Clear with this thing, geostationary orbit. Now these orbits, right? You can't launch a satellite wherever you want. And one more thing, when the satellite is about to get over, right? Sometimes countries do weird things also, like China one. What they did, their satellite is almost getting over, so they took a new missile, hypersonic missile, and they destroyed their own satellite. Anyway, satellite you have to destroy, so they wanted to test the missile. Can you hit a satellite in the sky which is going at a speed of 20,000 kilometers per hour? Imagine you're hitting something with a speed which is going at 20,000 kilometers per hour with your own missile. They're actually sending a warning to US, we can hit your satellites. And then we all condemned it. We said, yeah, you're polluting space. Actually, there's something called space pollution. All this debris that lands there are traveling with a speed of 20,000, 18,000 kilometers per hour. So if you see around the earth now, there are a lot of screws, bolts, all these particles, right? They're flying around the earth orbits. So anytime you launch something, one of them will come and hit and you get a hole in your satellite. So there's a lot of debris. So we are actually messing up the space also. It's called space pollution. I think another 30, 40 years, we will mess up the space sufficiently so that we won't even leave the planet. So what? You guys thought you're only polluting oceans and atmosphere. We won't even leave space. That is how powerful we humans are. Once we decide on something, we will, destroy it till the end. So humans are always like that. If you see, if you compare, there is only one more species like humans. You know what is that? A virus. A virus will attack a cell. It will multiply. It will consume all the resources. Then it will explode and spread to the other cells. And it will keep on spreading till the host dies. We do exactly the same thing. We go to a place, we consume all the resources, then we spread and we spread and we spread and wait till the planet dies. So there is a quote: Earth is a beautiful planet, but it has a disease called humanity. Unfortunately. Next thing, we'll be trapped on Earth. Then, yeah, Adrit, we will be trapped on Earth. We don't have an option. We can't go to Mars or Elon Musk. So, these satellites, we have a problem. You can't launch however you want. The main condition to launch a satellite, the center of the orbit should match with the center of the planet. Must be center of the planet. That means you have restricted actually. Suddenly the amount of satellites you can launch in a particular thing got restricted. Means you can launch like this, you can launch like this, you can launch like this. You can basically launch anything you want as long as this is the orbit. Reason? Think of like this. If you try to launch a satellite like this, what is the problem with this? The gravitational force is toward the center of the Earth. The centrifugal force is like this. They can never balance, isn't it? The forces won't get balanced. These are unbalanced forces. So you can't launch a satellite like this. So this puts even more restriction. Means you have very few orbits where you can launch. And on top of it, geostationary is even more special. A geostationary orbit must be in the equatorial plane. Just having 24 hours won't do. Meaning you are in a very specific orbit. Think of it like this. If you rotate with the Earth rotation, then you will think you are stationary, no? What if the satellite is going like this? Do you think it will remain stationary? You are going left to right and the satellite is going like this. You still think it is moving, isn't it? Geostationary, you think it should be at rest. So the satellite should rotate with the rotation of the Earth. So it should be in the equatorial plane. So that is one more condition. That means for the entire planet, we have only one orbit where it is geostationary. That is one more condition there. Clear? Turn the page. Now to cover a planet, let's say you want to use some kind of communication. We need minimum 3 satellites. Something like this. We need at least 3 satellites to cover this thing. But there is a catch. These things will occur, meaning if you think about it, this thing will cover exactly 120 degrees each, isn't it? Each one is covering 120, 120, 120. So that means these satellites have to be placed at an exact distance. So if this is R, this is 60, this distance has to be 2R. So you need 3 satellites at a distance of R from the surface. That is almost 6,400 kilometers. So if you keep them at a lower distance, so if you keep them only at a height of 200, 300 kilometers, you won't cover enough area. That's why you need more satellites. So basically you can cover up to that 60 degree square latitude angle. Clear? Next one. Turn in the page. Energy of a satellite. the potential energy is given by minus gmm by r. The kinetic energy is given by half mv square, where v is nothing but root gm by small r. This turns out to be gmm by 2 times small r. The total energy would be potential plus kinetic, which is minus gmm by 2r. So if you take the total energy is to potential energy is to kinetic. This was a question in the exam. Find the ratio of energies. -1 is to -2 is to +1. You know where else you see this formula? The energy of an electron in a hydrogen orbit. You get the same ratio there. So this is the total energy of a satellite. So be careful. A particle is at a height r. Potential energy is this. A particle orbiting at a height r, if you just use that word, orbiting at a height r, suddenly becomes this. So when you say it is orbiting, means it also has kinetic energy. And if you try to plot a graph for this, can you tell me which line is which one? What is the green line? Which energy? Potential, kinetic, total. Kinetic energy, positive. What about the red line? The red line is the total energy. Because if you see, the total energy is minus gm by 2r, it is a smaller one. The black line is a potential energy. That's more negative. It's a hyperbola. The farther you go, more negative it is. There. They would frame a graph like this and they'll ask you which line is what. And remember, all are hyperbolas. Clear? Turn in the page. Escape velocity. Is the minimum speed on the surface to escape to infinity. So if you launch a particle with you at an angle theta and finally it goes to infinity, energy is conserved. State 1, state 2. So initial energy is half mu square minus gmm by r is equal to 0. We get v escape velocity is root over 2gm by r. At infinity, we are assuming this is the minimum speed. This also is root over 2gr. Root 2 times v orbital. And best thing if you observe, this is independent of theta. It doesn't matter how you launch, you'll escape infinity. Now this escape velocity, root 2 gm by r, this is technically not right, but it kind of works. If this is less than equal to speed of light, is greater than speed of light. Means what? In order to escape this planet, you need to go faster than speed of light. But we know nothing can go faster than speed of light. Therefore, r must be less than 2gm by c square. This is a condition for black hole. If your escape velocity exceeds speed of light, meaning even light cannot escape. I know technically we can't use it for light, but gives you a rough idea like how small the black hole would be. There's a name for this thing. It's called a Schwarz. I think it's a German name, I guess. Schwarzschild radius, something like that. Do you know how small is this? If you take the entire Earth, and put it inside a tennis ball, you get a black hole. That is a kind of density we are talking about. Black holes are so dense. If you take the entire Earth and compress it and put it inside a tennis ball, you create a black hole. Just imagine, generally the radius of a black hole is 10 to 15 kilometers. How big the star must have been. So anything, any star just can't become a black hole. It has to have huge mass in the beginning only. And black holes are like massive and they are the monsters. They're like Thanos of universe. They come, there's only one thing to do, run away. Nothing you can do about it. Luckily in Interstellar movie, the guy goes inside and does all dances and all, but doesn't work that way.
There are black holes that are like so big, like a billion suns, like not like that.
The huge black holes are there. Every galaxy ka
But
middle
then
there's
how
a black
big,
hole.
like big will the star be?
Must imagine, na?
But is it even possible?
Why can't there be possible? The actually is more advantages. The bigger the star, the more pressure you have, more temperatures you have, the star will be more brighter. So we saw this in Wien's displacement of room, where blue stars are more hotter than red stars. Clear with this? Now, if I just give you a rough idea about these things, I'll tell you something. Now, again, this could be a paragraph question types. Life cycle of a star. So all stars, right? They start from nebulae. Nebulae are nothing but, these are huge clouds of hydrogen gas. And we don't know where these things came from. But they do exist. Huge. Matlab, I think the one recently I heard it is 3 to 4 million times the size of solar system. Something of that sort. These are huge. That's the radius, huh? The radius of that is 3 to 4 million times the solar system ka diameter, and then uska circle means imagine it's a sphere. Huge things, okay, nebulae. So these things are simply a lot of hydrogen gas ka cluster. Mostly they'll be in the form of hydrogen ions. So H atoms, let's say. Now what happens? Even though they're hydrogen atoms, there is a small gravity between them. Due to gravity, the gravitational force between them, all these hydrogens start forming a cluster. They come closer. So you will get they'll start clumping around. Now the thing is, once you start forming a clump, the mass becomes more dense, so you can attract even more hydrogens. No? So it's like a positive cycle. You do little work, you become strong, then you feel good, you do a little more work, and then you become strong, and you start pulling more and more and more. As you're pulling up more and more mass, at one point, right, this thing will reach a critical mass. So till now, nothing is happening. So what is happening here? The loss in gravitational potential energy, in this case, is a self energy, will become heat. So this self energy would be 3 gm square by 5r. Isn't it? Initially, all these are very far, so there's no potential energy between them. Isn't that how we define self-energy? You bring each particle from infinity and form this thing. So this would become equal to ms delta t, or you can say nc delta t. From here, we get a temperature. N is the number of molecules. We can calculate that. Once we got the temperature, now the problem for the hydrogen atoms is when you have a hydrogen and a hydrogen, both are actually having a positive nucleus and positive nucleus. They repel each other. That means hydrogens won't stick together. Hydrogen H2 is different. You're talking about nucleus level. Now, there is something called nucleus force. When distance becomes 10 power minus 15 meters, that is 1 Fermi, something called nuclear force will come. So we'll talk about that later on in modern physics, but there is something called nuclear force. Will come into the picture or will start acting. So nuclear force comes into picture only at a very small distances, to 1 Fermi. That means somehow you have to push this two nucleus up to 10 power minus 15 meters. If you can do that, they will fuse. So initially they're very far, so we're trying to put them to a distance of 10 power minus 15 meters. So initially this hydrogen is going with you, this hydrogen is going with you, and they're trying to get closer. And we know the kinetic energy of a hydrogen atom is nothing but 3/2 kT, Boltzmann constant. So this loss in kinetic energy becomes gain in electrostatic potential energy. So this is 3/2 kT. Again, I'm approximating a lot of things, but and this guy would become K, Q1, Q2 by the distance R. Here Q1, Q2 is nothing but electron charge because we're talking about one single hydrogen atom. And R is how much? 10 power minus 15. And we know T ka value from previously. So we can take the T and dump it here. So we get 3 kT is equal to, now we have to be careful, there are a lot of K's here. This is 4 pi epsilon. This is E square by 4 pi epsilon R. I will leave it like this. And R is 10 power minus 15. And we know the T ka value also from the previous one, which is 3gm square. 5 RMC. So substitute T here. From here, you'll get M. This M is your critical mass. So once you reach this critical mass, the hydrogen atoms fuse and they create helium. Hydrogen nuclei. So basically H and H will become helium. This is called nuclear fusion. And the star is born. And it starts producing heat. And you see that glow. So if you see currently our sun has around 75% hydrogen and 25% helium. Based on that estimate, you can find out at what time the sun has started. You're getting this? So the thing is, what stops, if you think about it, Jupiter is actually an incomplete star. We didn't have enough mass for the Jupiter to become a star. So if you take somehow mass from somewhere and pump into Jupiter more and more and more, at one point Jupiter becomes a star. So what stops something from being a star is the amount of mass you have in nebulae. If you have enough mass, if you are just combining, the end stage is you will become a star. If you don't have enough mass, you will just become a gas planet like Jupiter and Saturn. So you need to reach the critical mass to become a star. And once you become a star, this thing is happily glowing for a few years, few billions of years. And then at one point, the fuel gets exhausted. All the fuel on the surface gets exhausted, which is in this case hydrogen. Now, if the nebula has too much mass, what will happen? The helium will combine to form higher elements. Once the fuel on surface gets exhausted, the star actually shrinks. Because still now, because of high temperature, it is in expanded state. Once it shrinks, the gas which is trapped on the inner layers will undergo fusion. Now it expands from inside. The star becomes pretty big. We call it red giant. The star just expands from inside. Think of like an onion. Every layer is expanding from inside. Now, when sun becomes a red giant, the red giant will reach Venus. It will eat away both Mercury and Venus. It will become so big. And then during this process, sometime there will be a supernova explosion. We call it supernova. The star just explodes. And when the star explodes, the explosion happens two way. Some of the material flies off. This is what we call as explosion. But some of the material gets pushed inside. We call this thing implosion. And this force is so strong, the higher elements like iron and all, which, any element more than iron should not exist in nature. Later on, we will see. Energy wise, it is not feasible. It is less stable. But during this implosion, right, all higher elements more than iron are formed. We'll talk about that again, nuclear physics. That means every element that you think about, gold, everything is actually made during a supernova explosion. And then you'll be left out with some mass after that implosion. Now, if this mass is greater than 1.5 times solar mass, due to the gravity, the implosion, right, the electrons fall into the nucleus and you get a neutron star. Everything becomes neutrons. And if this mass m is greater than 3 times solar mass, it's called Chandrasekhar limit. An Indian scientist worked on this. These neutrons will collapse further into a singularity. You get a black hole. That is how a star dies. Clear with the whole story? You can make a small movie out of it. Mostly a documentary. But did you see how many concepts came? Self-energy, thermodynamics, KTG का 3 by 2 KT, electrostatic repulsion, nuclear fusion, nuclear force, every damn thing is there. Clear with the stuff. So something like this could be a paragraph. Okay? Take a break, come back with 7.5. That's the life cycle of a star. Chalo, come back in 10 minutes. Yeah, comes on everyone. Let's start off. The next thing, the trajectories. Consider a particle projected with speed u tangential to the surface. So case one, if your velocity is less than v orbit, you will go in a path like this and you will land on the planet again. So basically you get an ellipse. That means remember in projectile motion, we thought it is a parabola if g was constant, whereas in reality it is actually an ellipse. So if you're launching, ICBMs or nuclear missiles or any missiles from one point to another, you actually have to calculate an elliptical trajectory. So it's not parabolic, where the center of the planet will be the focus of the ellipse. If you launch with where u is equal to exactly v orbit, you will go in a circle. These things, there is no need to prove this thing. We can actually prove with the velocities. We can get eccentricity in terms of velocities. We'll not get there, it's too much max. Next thing, if your speed is less than v escape, but greater than v orbit, this time you'll go on one more ellipse, but this time it is a bigger ellipse where you don't collide with the planet. Focus will be outside. There'll be two focuses anyways. The center is one of the foci. Again, you get an ellipse. If you have u is equal to exactly v escape, or if u is greater than v escape, This is a parabola. This is a hyperbola. There, you get literally all your conic sections.
So in the V orbit is less than U,
Hmm.
less than V escape. C wala.
In view orbit.
C wala case. In that the elliptical path will be like on the planet या उसे ऊपर जाके होगा थोड़ा.
It will not collide with the planet.
So it will just graze over the planet.
It will just graze the point where you launched it from. ना वही तो graze करना ही पड़ेगा.
So in all the cases, it will reach the point where we launched it from now.
It's a
Okay.
closed orbits. Na? In the first three cases, they're closed orbits. So if you're launching from there, you have to come back there. Only in D and D, they don't come back.
Can I show the previous page?
So do remember the result. This was something like this was asked in bits. Bits or CET, I guess. I don't remember. They just gave the velocity and asked what is the orbit. Clear? Great. Let's see a question. The force between a planet and the satellite is given by F is equal to minus C R power N. C is constant. Negative indicates attraction. N is some number. R is a distance from the center. So instead of G by R square, the force is some R power N. M is the mass of the satellite. Find time period. Find velocity. Find total energy. And find N for stable orbit. Find the condition for a stable orbit. Meaning you can't keep N ka value whatever you want. There is a limit. So what is that values of N for which the satellite is stable? Let's get this. This is how they'll frame questions. So what I showed you is like theory and problems also. That is for GMM by R square. If this question comes in the exam and you want to guess, how will you guess?
So we can put N equal to -2.
Put N is equal to -2, you'll get all your standard results. Isn't it? So let's try. 2 by root m by cr power n minus 1. Yeah, something like that. I'm more interested in the condition for stable orbit. That would be a good one. Yeah, time period. I think most of you got it. Give me n ka value. That is what I'm more interested in. I'll show you the time period. So this thing is going in some radius there. The minus indicates attraction. So this force would be C into R power n. The centrifugal force would be mv square by R. So C R power n is mv square by R. We end up with V is equal to root over C R power n minus 1 by m. The time period is 2 pi R by V. That you can dump it, you'll get the time period and velocity.
तो n+1 होगा ना?
Mhm.
And
Yeah.
plus one होगा.
N plus 1. N less than nail, Lakshika. That's not the answer. Find the total energy. How do you find total energy? Now, total energy has two parts. First thing, we know force is equal to minus C R power n. Force is nothing but minus du by dx. So du will be C R power n dr. We get the potential energy C R power n plus 1 by n plus 1. Kinetic energy is half mv square. That would be CR power n plus 1 by m. Therefore, the total energy will be potential plus kinetic. Main thing is that you have to calculate the potential energy. This would be C R power n plus 1. You can take out common. You end up with 1 plus by 1 by 2. And we know total energy should be less than equal to 0, no? Less than 0 for to be bounded orbit. Not equal to also. If it is equal to, it will fly off to infinity. This should be less than 0. For stable orbits, total energy should be negative. That is a catch. Total energy is negative. So 1 by n plus 1 should be less than minus half. This y would be 2 is less than minus n. So n must be less than minus 3, na?
तो greater than -3 होगा ना?
That minus n का कुछ है ना? Yeah, n greater than होगा minus 3. That means values like -3, -2, -1, 0, 1, 2, 3, all these are acceptable. Why do you need to stop at -1? Mathematically, हाँ रमेशा, any particular reason you think we should stop at -1? इसमें कुछ issue हो रहा है?
तो सर ln n आएगा ना?
That is for n-1 ना?
हाँ
Yes, sir.
सर डिनोमिनेटर में भी n+1 है ना, तो टोटल अगर we take LCM then inequality would be like n+3/2 into n+1
नहीं,
less
एक और reason है actually. It should stop at -1. One more reason, because यहाँ पे जो constant है ना, we take infinity by 0. Potential energy at infinity should be 0, right, for reference. There are two things actually. So this is one reason here. Actually, this we didn't do completely. We got potential energy here. We take from R to infinity, na? Remember, what we got is potential energy here. We didn't get potential. This is C R power n plus 1 by n plus 1 plus some constant. For constant to be 0, we need potential u of infinity should be equal to 0. That is, when you put R tending to infinity, we should get 0. Meaning R by n plus 1 should be what? Therefore, n plus 1 should be a negative number. Getting it? So it should satisfy both the conditions. Therefore, n ka value should lie between -3 to -1. Are you getting the logic here? देखो limits यहाँ पे ना, how do we keep limits? We keep the limits from this is the potential energy u of r to potential energy to u of infinity. I mean, these are limits from r to infinity. If it is r power n, if it comes in the numerator, energy becomes infinity, right? So in order to get u of infinity 0, that should be giving us 1 by r में आना चाहिए. So 1 by infinity will become 0. So u infinity is 0 at r infinity. Is this clear, everyone? That is the reason why n is greater than -1 but less than -3. Because if you say, you'll get ln and all, then you can only say n is not equal to -1, na? Why can't I have n 0? Are you getting the reason? I'll just give an example. देखो, अगर सोचो force is -cr square, then when you write the potential energy du by dr, minus sign is -cr square. You get du is equal to cr square dr. So when you take normally potential energy, you got potential energy difference, which is c. So what will you take reference here? Let's say infinity to r and infinity to r. This guy would be, so potential energy at u of r minus u of infinity. This would be c r cube by 3. Limits go from r to infinity. This will blow off to infinity, isn't it? But if this had been f is equal to, let's say, minus c by r square, then the potential energy will be du infinity to r. This would be c by r square dr infinity to r. That would come out to be 1 by r by 1 by infinity. So that is fine, na? 0. You're safe. You getting the difference? If you have c in the numerator, if you have r power 1, r power 2, these systems, right, are like, you're getting energy will not be defined at infinity. You can't take infinity as a reference. Clear? Anusha, did you do the same thing, or I mean,
I
you
did
said
it
this
by
and
maths actually, like, yeah. I
uh,
didn't think of this. So,
uh, okay. Clear, everyone? Ishan got it? Utsa? Ishan, you
So I
still look
have one
confused.
question here in this.
Uh,
If n goes less than -3 and our c goes negative, we can still say the same now. We hold
C को
होगा.
constant रख लेते हैं ना रे God. नहीं, see, if C
I'm
becomes
holding
negative
the
means
door
force
number here.
become positive, na? If
Sir, to
C
make
becomes
mathematics of the
negative,
doors.
force becomes positive, right? Hello.
Sir, I have to get the door. I'm so sorry.
Next thing.
Yes, sir, I'm back.
Yeah. Next thing,
I didn't
elliptical
get you,
orbit.
sir. I didn't get you in this. In the
So
previous
we have the
question.
sun here.
Hello, sir.
Hello, we can't hear you. ठीक है. We'll talk after the class.
Okay, sir.
So we have, I didn't draw it properly again. So here the particle is there, here the particle is there. Let's say this guy is going with V1, V2, which I don't know. So sun is somewhere here. This distance is R1. This distance is R2. Mass of sun is m. Mass of satellite is small m. It's going in an elliptical orbit. The sun is actually at the focus. R1, R2 are given. What are these things called? Apogee, perigee, there is something like that. So the first question, find V1 and V2. V1, V2 are not given. You have to find them. What is the velocity at the farthest point and the closest point? Let's call this point B and let's call this point A. B, find the total energy of the satellite. This is a good formula. Energy of a elliptical orbit. We derived for circle, that was easy. Elliptical orbits also have an energy. Find the total energy of the satellite. Find radius of curvature at A and B. The only information you know is R1, R2, capital M, small m. Boss, you know only this much. Let me add you one more. If the minor axis is B, find time period of one revolution. This I could have done even after Kepler's law also. Okay. We'll do this in Kepler's law. Let's get the first three. Elliptical orbits. Anika, something like that. Looks right. Get the total energy. That is, I'm more interested in total energy. I think you should mug up the result also for total energy. Saves you a lot of time. It is easy to remember also. Again, standard stuff. You know this thing. You're not going in a circle. You're not going in a line. That's it. There is no other concept that you have other than momentum and energy. So brute force solving. This is your state 1 and this is your state 2. Now you have to simplify this time though. Conservation of linear momentum, m v1 r1 is equal to m v2 r2. We get v1 r1 is equal to v2 r2. Second, energy conservation minus gmm by r1 plus half mv1 square minus gmm by r2 plus half mv2 square. Take v1 from there and substitute here. Minus gmm by r1 half mv1 square minus gmm by r2. Half mv2 would be v1 r1 by r2 ka square. Small m will cancel. Bring all v1s to one side. This gm would be 1 by r2 minus 1 by r1. This would be half v1 square r1 square by r2 square minus 1. So v1 would be root over 2gm. This will be r1 minus r2 and that will be r1 square minus r2 square. That would give you r1 plus r2 in the denominator. And r1, r2 is there and r2 will go up. So this will be r2 and this will be r1. Check. Same way you can do with v2. V1 r1 is equal to v2 r2. You can substitute. So 2gm r1. This will be r2. This is r1 plus r2. You want to find total energy, you can choose any one place. Total energy is half mv1 square minus gmm by r1. If you simplify this, you get a pretty good answer, minus gmm by r1 plus r2, which is minus gmm by 2a. 2a is the major axis. Independent of the minor axis, meaning you take any kind of ellipse, the energy depends only on the major axis. I'll just put it in the next page. So if you have an ellipse, . . . and this is 2a. The total energy is given by minus gmm by 2a. Time period I still didn't teach you, but we will do later on. But let's write it down here also. Time period also 2 pi root gm a power 3 by 2. It depends only on the minor axis, independent of minor axis. Time period will prove with Kepler's law later. So exam mein, they framed a question like this. They said there is a circular orbit, let's call it 1. There is an orbit 2. There is an orbit 3. Like this, there were 3 orbits. The question was who has more energy, who has more time period, arrange them in descending order. Now you need to understand the difference between all 3 is this is the first one ka focus, F1. The red ka focus will be slightly to the side. The green ka focus will be here. So that is a catch in this thing. All 3 have different focus, but the minor axis is same. All of them have same minor axis. They have same time period and same energy. Quite an important thing. This is your minor axis, na B. Yeah, they have same major axis, so everything is same. Yes. So this is independent of B. So quite a useful result. So energy, so we proved it here directly. R1 plus R2, which is the two-way distance. It doesn't depend how thick is that ellipse. So quite a useful results. Please have a look at this page. Clear? Question is still not over. We have to find radius of curvature at A and B. How will you find that? Find the radius of curvature at A and B. Most people do this mistake. They think R1 and R2 are radius of curvature. Radius of curvature is something else. Radius of curvature is at this path. If you draw a circle, this is the radius of curvature. Radius of curvature depends on the trajectory. It has nothing to do with the sun or the R1 and R2. We did this in circular motion. How to find radius of curvature? Try, take a minute. Luckily, A and B will have same radius of curvature by symmetry. 2R1 R2 by R1 plus R2. Maybe that looks right. Radius of curvature में GM नहीं आएगा रे God. Dimension match नहीं हो रहा है. Yeah, radius of curvature. This is what we do. So when the particle is here, what is the force of attraction? G m by r1 square. So this should be equal to m into a centripetal acceleration. So from here we get a centripetal is gm by r1 square. So this should be equal to v1 square by radius of curvature, which is gm by r1 square into v1 square. That's how we get it. The net force on the particle, you know, attraction, that should be equal to the m into a centripetal acceleration. A centripetal is v square by the radius of curvature. And v1 ka value I know, I can substitute. Gm by r1 square, and v1 square is how much? 2gm r2 by r1. I wrote wrong now. v1 square by gm r1 square. There you get a good answer. R1, R2 by R1 plus R2. That's your radius of curvature. This will be the same as R2 also. 2 आएगा क्या? 2 भी आएगा. Yeah.
तो आएगा.
I hope you're getting it. Be careful. Radius of curvature is something else from R1 and R2. Quite a good question. Elliptical orbits. These are not standard. But this was a pretty good question, huh? They did ask this in the exam. They gave 3 orbits and everyone is confused. Like, energy was same, time period is also same. The difference is the focuses are different, but okay. Any doubts on this? Next one. Next one. We have a planet, mass m, radius r, and we have a satellite which is orbiting in a 3R orbit. So this guy is happily orbiting. Then some debris. So this is going with, let's say, some speed u. Should I give the same speed? Let's say this thing comes with speed u by 2 and hits the satellite and gets stuck. E is equal to 0. A rock of mass m by 2. एक काम करते हैं क्या? I can change this, but ठीक है. Collides with a, meaning there is a question you can frame like this. Find the condition if the satellite escapes to infinity. So fine, anyway, that we can prove it up. With satellite orbiting in a orbit of radius 3r. Now here there is one word you have to be careful. Huh? If I say it is orbiting in a radius of 3r, mean distance from the center is 3r. Sometimes they will say it is orbiting at a height of 2r. Means it is r plus 2r. So that word, be careful. Huh? I saw many people getting trapped. If they say satellite is at a height of 2r, he's saying from the surface it is 2r. If I say orbit of radius 3r, then it is done. So it's a perfectly inelastic collision. The rock gets stuck. Find the maximum distance of the satellite from the planet after collision. How do we do this? There, collisions. This is a very interesting problem where you use all 3 conservations. It's pretty rare to get all 3 conservations. Can I conserve energy initially? No, because E is 0. But can I conserve linear momentum? Yes. After the collision, can you conserve energy? Yes. After the collision gets over, you can conserve energy. This guy won't go in a circle anymore. Get me the equations. Solving might be, I don't know, you could have. But let's see the first part. Did you get it? So this is your system mass m going with u. This guy is m by 2 coming with u by 2. This is before collision. After collision, this mass becomes 3m by 2. This velocity becomes vx. This velocity becomes vy. Conservation of horizontal momentum, mu should be equal to 3m by 2 vx. So vx will be 2u by 3. Conservation of vertical momentum, m by 2 u by 2 should be equal to 3m by 2 vy. So vy is equal to u by 6. That's the velocity of the combined mass after collision. This is just after collision. The gravitational force is non-impulsive force, so you can. Now this guy won't go in a proper circle. It won't go in a circle. Now the velocity has become like this. This will start going in a ellipse. So now from the planet, you'll have a farthest point here. Again, remember, you have to come back to that same initial point. वो तो है. So somewhere here, I'm not drawing it properly, but this would be your farthest point. Let that be R. So this is your state 1 and this is your state 2. Have a look at it here. So now you'll conserve angular momentum and conserve energy. After the collision gets over, energy is conserved. Energy and angular momentum are conserved. Just write the equations and leave it. So angular momentum L initial is equal to L final. So L initial would be 3m by 2. Distance velocity is Vx. Distance is 3r. Should take only the perpendicular things. L final would be 3m by 2, final velocity V, and this is R max. That is one equation. Initial energy is equal to final energy. The potential energy minus G, 3m by 2 minus Gm, 3m by 2 by distance is 3r. That's your gravitational potential energy. It's an impulsive force, right, Aditya? It's a non-impulsive force, right? You can just conserve. It's like, suppose if a ball m and ball 2m, if they collide like this vertically and gravity is there, remember, it's a non-impulsive force, meaning you can neglect that for small time dt, you can neglect. Because the forces involved during collision are much larger. You can conserve just before and just after. That's why, see, after collision, linear momentum is not conserved. Linear momentum is not conserved because now it is under the external force. Write it on the next page. Initial energy is equal to final energy. So this is minus gm. Mass of the thing is 3m by 2. Distance is 3r. The kinetic energy is half 3m by 2 vx square plus vy square. Remember, both the components are there. Minus gm 3m by 2. This is your r max plus half mv square. There. Equation 1, equation 2. Can substitute and finish it off. That's what I said. This is a question where you have all three conservations. So before collision, you can conserve linear momentum. After collision, you can conserve linear angular momentum and energy. A rare case where you get all three conservations. Generally, we are in a habit of seeing two conservations at a time. Have a look at this. Any doubts on this? All clear? Last one. So we have a satellite which is orbiting with speed v. Let this distance be some 2r. Now, rocket engines, right? How they work? Rocket engines generally, when you are launching something into the one planet to another or anything, they just don't switch on the rocket engine forever. That's a very bad way to use it. Generally, rocket engines work in bursts. Meaning you just switch it on for a few seconds, then stop it again, then switch it on for a few seconds and stop it again. So you can time that. Small bursts of time. So every time you switch it on and switch it off for that small time, it gives an additional velocity delta v. It doesn't give you additional energy, it gives you additional velocity delta v. How? Do you guys remember in the rocket thrust force ka formula? F thrust is minus u relative dm by dt. This was a constant force. It doesn't depend on the speed of the rocket. It depends on with what speed you're ejecting the gas. So if you're applying for a small time, fdt, that will give you a small change in momentum delta p, which is m into delta v. So if you switch on the engine for few seconds, this is that additional gain in speed. So this is a very interesting thing. So when you switch on the engine, you're not gaining energy. What you're gaining is actually speed. So that means you can get different amount of energy depending on when you switch it on. Right? So find max distance after the first burst. Just write the equations. You won't be able to solve. I give all variables. Second thing, after the first burst, where should I start the engine again? At which point the engine should be, should be on to gain maximum energy?
सर अभी आपने बोला कि एनर्जी गेन नहीं होती.
Did I say that? Or did I
Yes,
say
you
energy
said
is not conserved?
so you said कि energy does not change.
I said velocity will change, energy gain can be different. You should not think like rocket engines give you energy, rocket engines give you velocity. Getting at which point engine should be switched on. Remember that. Switched on to gain max energy. Energy, so you will get it. But you shouldn't say every time I switch it on, that energy is being gained. You are getting velocity. वो उसका है. But the thing is, how many bursts are required so that this escape the planet? Find the minimum number of bursts. So this question, what I'm teaching you now, they made a complete movie out of it. वो है ना that movie, which one? Akshay Kumar का. They launch a
mission
satellite, Chandrayaan, I guess, Mangalyaan. This is that whole concept of that movie. Then I'm sure they don't know about this, but yeah. Try. Think. If you got the first one, you'll get everything. Just you have to write the equations. No need to simplify. So the interesting thing is that you will gain velocity and not energy. Now, again, when I say that word, it doesn't mean you won't gain energy at all. The main thing is it always gives you more velocity. So energy आएगा automatically. The first part was easy.
For 2 minutes not working.
Try. So let's say you are given velocity somewhere here. So when the engine starts now, so at this point the speed becomes v plus delta v. So you won't go in a circle anymore. You will go in a elliptical orbit. But again, you'll come through the same point. So this would be the farthest point, v final. This is the center of the planet. So this was 2r. This would be, let's say, r1. So conservation of angular momentum, mv plus delta v. 2r is mv final r1. So r1 is the distance after the first burst. Conservation of energy, half mv plus delta v square minus gmm by 2r, will be half mv final square minus gmm by r1. You can substitute here, you'll get r1 from here. This is the distance after the first burst. Now try to understand here. Every time what you're giving is gain in velocity. So think like this. Let's say your kinetic energy. Example, I'm giving you a number. Let's say half m 100 square, or another situation you have half m 50 square. Now if I increase both of them by number 1, who will have more change? If 100 becomes 101 square and 50 becomes 51 square, in which case did you gain more energy? 101 square, isn't it? That means you should switch on your rocket always at the point with the maximum speed. You're getting it? When you're going in an elliptical orbit, if you observe, this V final is the minimum, no? This is your minimum speed in the orbit, isn't it? This is your maximum speed in the orbit. And every time you're giving an additional speed, the simple number, let's say you have speed 20 and speed 40. If I increase this by 1, I can increase this by 1. This will be 21 square, this is 41 square. What is the gain? This is 21 square minus 20 square. This is 44, 41, 41. And what is this gain? 41 square minus 40 thing, how much is that? 1 and 2,
51.
164, no? No?
But
How
81
much is
won.
that?
81
41 minus 1, 41 plus 1, na? हाँ, 81.
A square
So
minus b square.
ये कितना होगा? That is right only, na? 41. So there you can see you gained more energy, isn't it? So gain in kinetic energy is half m v plus delta v square minus half mv square. So if you simplify this, you end up with half m v square will cancel. 2 delta v into v plus delta v square. So this is m delta v into v plus m delta v square by 2. So there, gain in energy, right? So you can clearly see here, if you have more speed, you get more energy. If rocket engines are switched on at maximum speed, we gain more energy. Actually, we can find R1 very fast, you know how? ये सब करने का जरूरत नहीं था. Now it is going in an ellipse, right? What is the energy of an ellipse? Minus g mm by R1 plus 2r, isn't it? That becomes a major axis, no, for this ellipse, R1 plus 2r. So I could have directly calculated that, R1 plus 2r. This is your major axis. From there you get R1. So next time what will happen? So this is how the whole orbit would look like. Initially, if you go with speed v, you will go here. When you increase the speed to v plus delta v, you will go in a bigger ellipse. When your speed becomes v plus 2 delta v, you'll go like this. And then if you keep on increasing, and then if you keep on increasing, at one point you give enough speed, you're gone. So at this point, this is v plus n delta v. That is, n is the number of bursts. So half m v plus n delta v whole square minus g mm by 2r should become greater than equal to 0. The total energy becomes positive. Means it has escaped from the planet. This is how they launched the satellite to Chandrayaan, this Mars Mangalyaan. This is how they saved the fuel. Instead of using a rocket and continuously bursting towards Mars, which is very difficult and consumes a lot of fuel, they actually kept on sending this thing, round multiple times in the blaster. This is a concept also called as, gravitational slingshot. Ever heard about it? Gravity assist. What these people do, let's say you want to send something. This is what they actually did also. They wanted to send a satellite from Earth to Pluto. What these people did, instead of sending towards Pluto, they sent it towards Venus. So as this thing started approaching Venus, they used the Venus gravity. It started going in an orbit. When it reached maximum speed, they switched on the engine delta V, so it gained more energy. As it started coming back, the Earth which was there, Earth came into place. Now they used Earth as a second slingshot. It went around the Earth, it gained maximum speed. Again, they started the engine there. And again, you gained more speed. As it is going, then they used Mars, then they used Jupiter, then they used Saturn. So they were using each one like a catapult slingshots, and they finally launched it to Pluto. This thing saved the time by 3 years. It reached Pluto 3 years before the estimated time. So this is called gravitational slingshot. You can use the planets. This is called gravity assist. So the main idea and the concept is this. You use the planet's gravity, go to maximum speed, and then increase your engine for small time. You get more speed than normal. So instead of switching on the engine at a regular time, switching on engine at a maximum speed gives you more energy. Basically, it is like this. The amount of fuel you're burning is fixed. But how much energy you can extract from that fuel depends on this velocity. If you increase your velocity at low speeds, most of the energy will go in the form of heat. So there's a restriction there. Clear with this? So there. So next thing, what's left is Kepler's law. We will finish off with that in the next class, mostly in the first half, and then we will go ahead with waves. Okay, so this will wrap up for that day. So do make sure to go through these things. If you see nothing like this was done in electrostatics, all these are a little weird. So do make sure to go through all this stuff. Okay, so any doubts, anything, stay back, or else you're free to leave. So take care, stay safe. I'll see you guys next week.